Good afternoon, everyone. So, how was the test? The strength is very less. Only 25 students have joined. Hmm? Okay, let's start with the class. I hope you all can hear. I think I'm quite audible. Okay. So, last class we had discussed about the Bode plots. Do you remember any this Bode plot, or you want me to repeat it? Yes, I'll just get back to the screen. So, are you all okay with the next problem, or you want me to just repeat it once before I start off with the problem? Just leave a message in the chat box. As per that, I will go ahead with the class. Yes, should we repeat it, or shall we move with the next problem? Please reply in the chat box. Okay, I will repeat it. Okay. Okay, students, I will just give you a brief description of the previous class, what was done. Because last class I had just given you the introduction, and we had discussed about few steps in how to plot the Bode plot. So I have just got a message to repeat that. I will do that, and we will solve one problem also. Okay. So these theory things I will not just do it. I'll just go straight away with a problem, example, steps, and then with a problem. Okay. So basically, Bode plot, we just knew what was the definition for a Bode plot. It is a frequency domain technique, and we have two factors to be considered here. One is the magnitude, and the other one is the phase. So magnitude plot and phase plot. So Bode plots, you just have to know that you have to plot two things on a single graph. One is magnitude followed by a phase. Okay, so that you should know. So process to plot the Bode plot, I told you there are various steps which you have to follow. So in the step one, I told you that you have to bring down the given transfer function to a standard form. If it is already in the standard form, then you need not have to do anything. How will you know that it is in the standard form? When you have this constant k, this k talks about the gain. So when you know this k is there in the problem, then directly you can just go away with this step two. If not, you have to convert the transfer function into the standard form where you will have this k, a constant term present, which will be useful to find out the gain. So that with the gain you can plot the magnitude. So that is why we have, and this is one more thing that you will be doing here. You will just take out the corner frequencies as common outside, because those corner frequencies will form this parameter called k. So I told you that when you have this system where uh, you can see in the denominator there is no s term, just a single s is not present. If a single s is present in the denominator, it says that s is equal to 0. That means there is a pole at the origin. But since there is no pole at the origin here, I can say that this is a type 0 system. So that we discussed last class. For type 0 system, there is no pole at the origin, and slope of the first line will be a 0 dB line. For type 1 system, you can say one pole will be at the origin. So you should have one single S parameter followed by these terms. So if you have one pole at origin, then we call that as type 1 system. Now, step two. So first step, what is that you have done? You have just boiled down the given transfer function equation to a standard form. Okay, and then you have found out what is the gain there, the gain value, and after that you have to go for step two. What is step two? Identify gain and slope of the first line. So I told you that if 10 is at origin, then slope of first line will be plus 20 dB per decade. If one pole is at origin, then slope of first line will be minus 20 dB per decade. That means the terms which are present in the denominator will give you a negative decibels per second, and the terms which are present in the numerator, which will indicate zeros, will represent the positive values of dB per decade. And those dB per decade, whatever values you get here, those are the slopes of the first line to be drawn on the Bode plot for the magnitude curve. So if two poles are at origin, then slope of the first line will be minus 40 dB per decade. So every pole will be minus 20 dB per decade, whereas every zero will account for plus 20 dB per decade. So if you have two poles, then it is minus 20 plus minus 20, which will give you minus 40 dB per decade. If there are two zeros in the numerator, then it will be plus 20 plus 20, that will be plus 40 dB per decade. So this is how you determine the and what is the determine the slope of the first line based on the roots which are present in the numerator as well as the denominator. Okay. So based on k, so now since you know k, we can calculate gain at frequency omega, which is equal to 1 radian per second. So this is the standard frequency that you will consider, where omega will be 1 radian per second. So gain will be equal to 20 log k at omega equal to 1 radians per second. So now whatever value you would have got for k, you will substitute that value here and you will find out the gain in dB per in dB. Okay, in dB. Then third step will be arrange all frequencies in ascending order and define slope to each line. So I told you that based on the number here, suppose you have corner frequencies, say A as 1, B as 2, Q as 3, and P as 5. Then that will be the ascending order of the frequencies that you are going to arrange. Okay, and then why we call this as corner frequencies, that I will tell you when we are drawing the Bode plot. Okay, now so A here was present in the numerator, so it is a 0. And what is the first line slope of that? Okay, sorry. Here the first line slope will be 0 dB per decade, since there is no pole or a 0. Okay, let's not worry about this. Just see here. W is equal to A is a 0, which indicates it is plus 20 dB per decade. Then W is equal to B will be a 0, which will be plus 40 dB per decade. Okay, how did you get this plus 40 dB per decade? You are just adding with the previous this one. So 0 will have plus 20 dB per decade. and that will be added by the previous value, which is plus 20 dB per decade. So that will give you a resultant value of plus 40 dB per decade. Then for a pole, again, for a single pole, it is minus 20 dB per decade. And what is the previous value? It is minus 40. So you should add those two. So minus 20 plus 40 will give you plus 20 dB per decade. Then omega is equal to P pole, it is minus 20 again and plus 20, which will give rise to 0 dB per decade. So at this frequency, it is plus 20 dB per decade. At this frequency, it is plus 40 dB per decade. At this frequency, it is 20 dB per decade. And again, at the final last value of frequency, the value is 0 dB per decade. So now identify slope with all corner frequencies. We have to do algebraic addition of slopes which are the same thing. Whatever I explained you, it is written in theory here. Then step 4. Now since that now you know, this will help you in plotting the gain or the magnitude part of the Bode plot. Now to get the phase part of the Bode plot, you should know the equation for phase plot and make a table for phi at omega. So phi is given by the equation plus tan inverse of omega by a. You can see plus positive sign will be for zeros which are present in the numerator. So plus tan inverse omega by a plus tan inverse omega by b minus tan inverse omega by p minus tan inverse omega by q. So these negative signs are for the poles which are in the denominator, and these two positive signs are for the zeros which are present in the numerator. Then just tabulate those values. For omega, we will usually take it as 0.1. Why? That is because in the logarithmic scale, if you take the value of omega as 0. If you start, you can ask me why not 0 and why you have considered as 0.1. When I put omega value as 0, log of 0 will give you what? It gives you infinity. That's the reason we are not going to consider that. Okay. So either you can start with 0.01, 0.001, 0.1, anything as per your convenience. But usually in all the textbooks where we have come across, they have taken this 0.1 as the starting frequency so that it will be easy for us to plot the graph. So that's why I too have considered this value of 0.1 for omega, the starting value. And for that particular value of omega, and since you will be knowing these values of corner frequencies, you can easily compute this angle, that is the phase angle phi. So for some few values, you can just compute. It will go on like 100,000, 10,000, 1 lakh, and so on. So for those values, you can compute the phase angle. So once that is done, I told you that these are the parameters in the Bode plots. So there are 4 different parameters. Okay, so this is a Bode plot. This is a graph which we are going to plot in the semi-log graph sheets. Okay, and I told you that both magnitude and the phase part of the graph will be plotted on a single semi-log graph sheet. And here, usually first we plot the magnitude part and then we plot the phase part. So the magnitude part will be magnitude in dB versus frequency. Okay, and then you can see that we will just mark these points as plus 20 dB, plus 40, plus 60, and below 0 it will be minus 20, minus 40, minus 60, and so 0 dB will be the reference line for this graph. Okay, then we can see here the 0 dB per decade line means what? See, from 0 to 1 will be one decade. Okay, from 0 to 1 you will have 10 divisions in the graph, so that will be taken as one decade. 0 dB means there is no slope, so it is just a straight line. Okay, 0 dB will be just a straight line. Suppose I have my gain, say suppose I have got my gain value as plus 20 dB. So from 0 I will just go above for plus 20. From here I should start seeing for the next frequency, that is at omega is equal to 1. I will be having if I do not have any slope, the first line slope will be 0 dB. Then this will indicate 0 dB per decade. Then from here, you can see that from here, this is the, so this point will give you one frequency now. So this starting point was omega is equal to 0. Then omega is equal to 1. So at omega is equal to 1, there is this is one corner frequency, because from here again, we will consider roll down factor, that is minus 20 dB per decade, and this will go down. So here from omega is equal to 1 to next decade, that is omega is equal to 10. From omega is equal to 1 to 10, this will be one decade. And you can see that since you have a slope which is coming down from this straight line, it comes down. So this is taken as minus 20 dB per decade. It is coming from plus 20 to this zero line. So it is minus 20 dB per decade. Why? Because from omega 1, you should move one decade, and for that decade, you should draw one line which is minus 20 dB per decade. This is a slope. Suppose from here, if I was going up like this, then that would have been given as plus 20 dB per decade. Now, this is also one more corner frequency, and I told you that whenever the slope crosses this 0 dB reference line, that is called as the gain crossover frequency. So omega GC indicates the gain crossover frequency, where magnitude plot of Bode plot crosses 0 dB reference line. So now this you have got again when you are getting minus 20 dB. Okay. So here they have given for corner frequencies, I guess minus 20 minus. Let me just see here what is that. Okay. So first line slope line was 0 dB per decade. So at 20 dB, they have taken here as 0 dB per decade. From there, okay. So they have not taken this as an example. They have just roughly shown what is plus 20 and what is minus 20 dB. Okay. So this is just, they have just shown what is meant by plus dB, minus dB, what is gain crossover frequency, what is this phase margin, all that. So let me just explain all of that in this. They have not related this with the previous values that we have found out. So here, so 0 dB means it's a straight line. Minus 20 dB means it goes down. Again, you have a minus 20 dB which is going down with one decade. That is from omega is equal to 10 to this might be omega is equal to 100, this point. So till there, again you are getting a minus 20 dB line, and from there you are getting a 0 dB per decade line here. Okay, so all these points are called as corner frequencies. At these corner frequencies, you will be seeing what is omega. Omega is 1, omega is 10 here, omega is 100 here, like that. Then, once you find out this gain crossover frequency, just from there you drop a line, a dotted line, and see where it is going to cut this minus 180 degrees reference line. So that minus 180 degrees reference line where it cuts, and from there, from that line to this curve where we have got this graph for the phase. How do you get this graph? By you have already plotted this, right? The phase angles at 0.1 you have one angle, at 1 you have at omega is equal to 1, that is at this point you have one more point of phase. So when you drop those points and when you join those points, you get a curve like this. Okay, so from gain crossover frequency, if you drop a line, you will find phase margin. Then similarly from the phase crossover frequency, when you draw a line extending upwards, you will get a gain margin. So that is how we find the gain crossover frequency, phase crossover frequency, gain margin, and phase margin. Once you find out all these parameters, you have to comment on the stability of the Bode plots. So for stability, commenting on stability, you should know these three conditions. So if omega GC is less than omega PC, then it is a stable system. As I told you here, this is omega GC. You see here, this omega GC point is at a farther away from 0 point, whereas this is much closer to this 0 point. That means this frequency is now less compared to omega GC. So when omega PC is less than omega GC, we call that system to be an unstable system. Okay, so that you should take it. So if you want to make the system stable, then this point should be either this point should be moved ahead of this PC, or this point should be moved after this omega GC point, so that you will get this condition of omega GC less than omega PC for stable system. So that is about the stability of Bode plots. Advantages I've already spoken about it in the last class. So that was one general form. And here they have taken one example. Now this is one transfer function which has been given. As you all can see here, it is not in a standard form because you do not have any. So what is that you have to do? You should take 1 by 10s. So here how do you take that? 10 is taken out as common, so do all that and you will get a constant k which is 1 by 10. Then find out the gain at omega is equal to 1 radians per second. So you will get the values minus 20 dB. So then the steps, all those whatever I have discussed there, the same steps have been written in very briefly here. And then they have given the definitions for omega GC, omega PC. GM, PM, then stability. So all that we have discussed there. So this was about the introduction to Bode plots. So you have any doubts? I'll just come back to the screen. Yes. Any doubts? Okay, so no doubt. So just we will take one problem, a complete problem, and see how to do it. Okay. Okay. So let's take one example. So all of you please have one book and paper, pen and paper to write down these. I will give you one problem to be solved. And as I told you, now the shops are open, right? So you can just get some similar graph sheets with you. Okay. So now just see here. I'll go slow with this problem. Draw Bode plot and comment on stability for given system. So g of s into h of s is given as 100 into s plus 3 divided by s into s plus 1 into s plus 5. So now this you have to bring it to a standard form. So standard form, how do you do that? Just take out this as common. So you should be getting something as 1 plus something like this. Okay, this will be the standard form. So when you do that, so here I have taken in the numerator 3 as common. I've taken it out. So you will get it as 1 plus s by 3. In the denominator, you can take out 5 as common. So 5 into s into, even if you take 1 as common, it will be still 1 plus s into 1 plus s by 5. So this will give you how much? 60 into 1 plus s by 3 divided by s into 1 plus s into 1 plus s by 5. So k is equal to 60 is a constant. So now gain at omega is equal to 1 radian per second for first line. How much do you get? 20 log k, which is 20 log 30. So you will be getting the gain value at omega as 1 radian per second to be 35.5 dB. So you have your calculators with you. You can just calculate this and you can. So say there is no base given. That means you will be taking it as to the base 10. 20 log 60 to base 10, which will give you 35.5 decibels. So this is the gain value. Okay. Now make a table here. So frequency, pole or zero, slope and resultant with 4 columns. And I told you that you have to arrange the frequency in ascending order. So what all frequencies you have, if you see here, you have a frequency which is 1, you have a frequency which is 5, you have a frequency which is 3, correct? And you have a frequency which is 0. So write down that. So omega is equal to 0, which is present in the denominator. So that is a pole and it will have a slope of minus 20 dB per decade. And what is the resultant since you do not have any other previous value? So you just retain this as minus 20 dB per decade. Then omega is equal to 1. So that is also a pole, right? Omega is equal to 1 is in denominator. So that is also a pole. So that the slope of that pole is also minus 20 dB per decade. But you will add this value with the previous resultant. So that will give you minus 40 dB per decade as a resultant for this value at frequency omega is equal to 1. Similarly, now omega is equal to 3. Where is it present? It is present in the numerator. So that is a 0. So what is the value of that? It is plus 20 dB per decade. So add this 20 dB per decade with the previous value which is minus 40 dB per decade. When you add, you will get the answer as minus 20 dB per decade as the resultant. Then omega is equal to 5, which is also a pole again, so whose value is minus 20 dB per decade. And now add these two values, minus 20 dB per decade with this minus 20 dB per decade. You will get the answer of minus 40 dB per decade. Now, so this is about, so these were the values required to plot the magnitude curve. Then, for the phase of the given system, to find out the phase of the given system, replace S by j omega. Okay, so 100 into 3 plus j omega by j omega into 1 plus j omega into 5 plus j omega. So the resultant phase will be what, whenever you encounter a term called j omega in the denominator, that will give you minus 90. So you have to write it down as minus 90. Minus tan inverse of omega by 1 minus tan inverse of omega by 5 and plus tan inverse of omega by 3. So this is the expression. Then again make a table, frequency versus the result, phase angle. Okay. So at omega is equal to 0.1, you will get the answer as minus 94.9. So like that at some intervals. So 0.1, 0.5, 1, 5, 10, 100, 500 up to 1000, you just do the angles. So once you get these angles, now is the part where we have to look into how to plot the Bode plot. So I will just share one more screen. Okay, now see this graph, all of you. So this is a semi-log graph sheet. So you can see here. So this is a semi-log graph sheet. You will have something like this. So here you can see there's a tiny, I'll just see if I can zoom. An option to zoom here. Okay. So see here, on the x-axis, you can see they have taken frequency in radians per second. So here, this point, a tiny value, I don't know whether you're able to see or not. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and again it is 1. That means if this is 1 to 10, again 1 to 10, 1 to 10 like that. So I have taken this first value to be 0.1, the frequency omega. So I have written here, this is 0.1, in red you can see. So this one, I have made that one as 0.1. Okay, so from 0.1 to next, I have taken the value as 1. So from 0.1 to 1, there are 10 divisions in between. Okay, so if this is 0.1, next value will be 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1. Then 2, 3, 4, 5, 6, 7, 8, 9 and this dark line you can see that will be 10. Then if it is 10, then next value will be 20, 30. You can see that there is unequal spacing. 20, 30, 40, 50, 60, 70, 80, 90, 100. Then 200, 300, 400, 500, 600, 700, 800, 900, 1000. Similarly, 2000, 3000, 4000, 5000, 6000, 7000, 8000, 9000, and one more darker line you will get where it can be written as 10,000. So this is about the x-axis. Coming to the y-axis, you can see that since we are going to plot both the magnitude and the phase angle, you can see that there are two curves. One is the magnitude curve and the other one is the phase curve. So on the y-axis, you can see that it is divided into two types. One is gain at dB in the upper half of the graph, and the lower half of the graph indicates phase in degrees. Okay. So now, first value, I hope this graph how to label this you now know. Okay. So now, here you can see, since the gain value I got it as uh, 35.5 dB, I will take the maximum value. The maximum value of the gain is 35.5 dB. So I have taken the maximum value here as just a minute. Okay. I will take this, you can stop, usually I will take this as plus 60 or plus 80. So in most of the graphs which we draw, we will take this upper value as plus 60 dB. Okay. So here this is 0. For you can see that there are one boxes here. So every box will indicate 20 dB. So this is 0, starting with a 0. You have 20 dB, 40 dB and 60 dB. Okay, these are all positive values, that is above 0 dB. Below 0 dB, again take it as minus 20 dB, minus 40 dB, minus 60 dB. In between 40 and 60, there are 5 lines. Okay, there are 5 lines in between 40 and 60 dB. So this will be a 20 dB, which will be divided 5 times. That means each line here will indicate a 4 dB line, I guess, if I'm right. Correct? Since you have 5 lines here in between this, and what is the value, what is the difference in dB? 40 and 60, what is the difference? It is 20. Here, difference between 20 and 40, it is 20. Difference between 0 and 20, it is again 20. And these 20 should be divided equally among these 5 lines. So each line will be of 4 decibels. Okay, so that is how you do. Now, so this part you have you now know how to mark the values. Now, first value, see here, gain, first you have to mark gain at 1 radian per second. So gain at 1 radian per second, we found the value to be 35.5 dB, correct? So 35.5 dB uh, at 1 radian per second. So 1 radian means this is 0.1 radian per second and this is 1 radian per second. So at 1 radian per second, from the 0 reference line, you have to come to the 0 reference line, and at omega is equal to 1 radian per second, you have to plot 35.5 dB. So you have to put a dot. So this is 20 dB, and I told you that each line is of 4 dB. So the next line will be 24, then next will be 28, then next will be 32, and then next will be what? Next will be 36, right? So below this line, just below this light color line, you can see, just right below that you have this dot, which indicates 35.5 dB, which is almost equal to 36 dB. Okay, so just put a point there. Okay, I hope you're all able to follow. Once I teach this, I will just come back to the screen. Then if you have any doubts, you can ask me. First, let me explain. So here, first plot this frequency on the x-axis in radians per second, starting with 0.1, 1, 10, 100, 1000, 10,000. Similarly, on the y-axis, first I'm interested in plotting the magnitude part. So I will just write gain in dB, starting from plus 60 dB, plus 40, plus 20, 0, minus 20, minus 40, minus 60. So here you can see what is that first thing that I did. First, I have to mark a point in dB for omega is equal to 1 radian per second. So 1 radian per second line is this one. So here I will be marking a point which is 35.5 dB. How did I mark this? From this 0 reference line, I have to go up to 35.5 dB and put a point there. Once that is done, what is that next thing you have to do? Now see here, the frequencies plot which we had done here. Now he says, see here, at omega is equal to 0, there is a pole with a slope minus 20 dB per decade. So omega is equal to 0 means what? We do not have 0, so we will take it as 0.1. So here, from here, from here, this is at 1, whereas this is at zero point 0.1. So somewhere here, you just see, from here, I will come back. Now we have got this point. From here, I will come back to this value of omega is equal to 0.1, because this is a decade. Decade means from 0.1 to 1, it is 1 decade, correct? So from this point, I will come back to this point, to this to this line. From here, from this point, I should go 20 dB per decade above, isn't it? Because at omega is equal to 0, you have to get a slope which is of minus 20 dB. But how do I draw that? I'm here. So go back one decade back, and then minus 20 dB means you have to go up here, because this line which we draw now will indicate minus 20 dB. Do not come down, because from here if I draw, it will become plus 20 dB, but my line is minus 20 dB per decade. So from this point, come back one decade, that is from 1 to 0.1 will be one decade, and it is minus 20 dB per decade. So come to this point, go back by 20 and draw a line here, draw a slope here. Now this slope will indicate minus 20 dB per decade line. Okay. Then once that is done, then you have drawn a line, a dark, you have darkened that line till from omega is equal to 0 till 1. That is from omega, starting from omega is equal to 0, but we do not have 0, we are having 0.1. Then now at omega is equal to 1, at this point again, what is that you have to draw? What is that you have to draw now? From omega is equal to 1 to omega is equal to 3, you have this minus 40 dB per decade, isn't it? So minus 40 dB per decade means what? Now from 1 to next decade, you have to go, I guess. One second, let's see this. Okay. From this, what is the next decade? It is 10, correct? So 10 is here. But see this, you have drawn this line here. Once you draw this line, you have to extend that line. Okay, so you can see a light sky blue color line which is extended. So from this darker line, just draw one slight light color line which is extending. Now from omega is equal to 1, just come one decade ahead, which is till 10. Then what is that you have to do now? You have to mark minus 40 dB. That means from this point, come one decade here. Now go down for minus 40 dB. That means from it is almost here, right? From here you have to go 40 dB down. So you will get somewhere here. The point you will get somewhere here. Okay. So if you go 40 dB down, then what is that you have to do now? Now this you have to just mark this point again. Now from omega is equal to 1, next value is omega is equal to 3. Now where is omega is equal to 3? This is omega is equal to, this is 1, this is 2, this is 3. So at omega is equal to 3, come down, okay, come down, and this line which you had drawn here, okay, what is that you do is you just join this point with this point. Once you join this point with this point, in a light, you just have to draw a light color line. First, you join this point with this point, okay? Then, now again go for omega is equal to 3, come down, you will get a dot here. So, what is that you should do is from this point to this point, darken the line, okay? Darken the line. Then, then from omega is equal to 3, again what is that you have? Minus 20 dB per decade. So omega is equal to 3. From here to next decade will be here, correct? From 3 to 30, this will be till here. Where is that 3? This is 3. So till here you have to go 40 dB down. So from here you have to go 40 dB down. Now from here come back one decade ahead. That is from omega is equal to 3. Come down one decade ahead. That is from omega is equal to 2. Now from omega is equal to 2, So whatever line you had drew from omega is equal to 3, you would have you can see the light color lines here. Okay, if you zoom in, you can see those light lines. So again, from omega is equal to 5, just where you have drawn this, extended this line right to that point, make a darker version of it. Then again from there, from omega is equal to 5 to next decade will be till 50. From there you have to go down by again minus 40 degree. So like that you have to do the graph. So I want you all to try this graph at home. Um, Once you just go through, so that's why I'm write down the rough graph of this and try it out in the similar graph sheet at home. So once you get that, now the lighter lines will just be remaining like that. Don't worry about it. Just darken the line. It should connect all these points properly. The darker line should connect all these points. Now this will give you a magnitude graph. Now you can see which is the point. Now this is the point which is crossing this um, positive dB to negative dB. Okay, that is, it is crossing the zero line. So that will be giving you gain crossover frequency. Now this point is at what frequency? It is at 10. So that is why you can see here gain crossover frequency is equal to 10 radians per second. Once you get this, now you can see here the phase in degrees. How is that we have written? We have taken it as minus 90 degrees, minus 120, minus y, because you can see here for frequencies omega is equal to zero point 0.1, omega is equal to zero point 0.5, omega is equal to 1, omega is equal to 5, 10, 100, 500, 1000. You have these values. So the first resultant value here you are not able to see because there is a sketch on this. It is minus 94.9 something. So since it is minus 94.9 something, I will be starting off with minus 90. And what is the maximum value? It has gone up to minus 179.8. So I have taken the maximum value here as minus 180 degrees. So now you can see I have taken a division of 30, difference of 30 degrees each. So this minus 90 degrees with a 30 plus 30 dB difference, degree difference. Next is minus 120 degrees, next is minus 150 degrees, next is minus 180 degrees. So based on these values, I have given the scale here. So I have given a gap of 30 degrees each. So now, so when I have a 30 degrees gap, and you can see that there are two boxes, correct? So this complete divisions, if you see, there are 10 divisions between this 30-degree line. So each line here will constitute a 3 degree line. I hope you're able to follow this. There is 10 divisions between 90 and 120. So uh, that is, there is a 30-degree difference and there are 10 lines between these two. So each line will constitute for a 3-degree line. So now here it is first value for omega is equal to minus 1. So omega is minus 1 here. In that line, I should now mark a point for minus 94.9. So somewhere here you will get. So that is why we have put a point here. Next value for omega is equal to 0.5. 0.5 means somewhere here. So for this point here, here you will have to mark for minus 112.7. Similarly, for omega is equal to 1, at omega is equal to 1, you have minus 127.9. So based on this, you just have to plot. So when you plot that, you will get these points. Just join all those points. Okay, and you can see, I don't know whether you're able to see this at the end. It is not touching the 180-degree line because it is maximum is minus, excuse me, maximum is minus 179.8. So it is going to just continue like that above the minus 180-degree line. It is not going to touch. That means it is just going like that and it is going to touch somewhere at infinity. So that is why, since it is not crossing that line, the minus 180-degree line, we will take the phase crossover frequency as infinity, since it is not touching that reference line. When this becomes infinity, then we can say that the corresponding line from omega, see, from omega GC, when you draw a line here, you can find out phase margin. But omega PC we cannot locate because it is just infinity. When this is infinity, the corresponding point will be gain margin, which will also be infinity. Now, this value, see here. Okay, see here. Now, this value, omega GC, you got 10 radians per second. Corresponding to this, you have this phase margin. From this point to 180-degree reference line will give you the phase margin. That line, that difference. So that is phase margin, which is 17 degree. Then phase crossover frequency is infinity. Gain margin is infinity. Here you have to know one more thing. If you get a gain margin below this 0 dB line, that will constitute for a positive gain margin value. Okay, if you get a gain margin corresponding to the phase crossover frequency, which is above 0 dB line, that will give you a negative gain margin. But in case of magnitude plot, it is opposite. So here, if you get a phase margin above this 180-degree line, that will give you a positive value. If you get a phase margin which is below minus 180-degree line, that will be a negative value. So here, whatever you should know this point properly, then the reverse will be in the phase angle plot. Now, here I cannot show you the value because gain margin is infinity. So that is why I cannot say whether it is a positive or a negative value, because you have got the value as infinity. But in future problems, if for the point phase crossover frequency, if you get a gain margin which is above 0 dB line, that will give you a negative gain margin. If it is below 0 dB line, then you will get a positive gain margin. This you should remember. Now here for this problem, you can see that the phase margin, which is infinity, is greater than the gain margin. So this is the condition which is needed for the system to be stable. So we can call this system to be a stable system. So this is about the Bode plot. So I'll just come back to the screen. Many have left the meet. Very good. Okay. So any doubts? Don't worry, I will explain some more problems so that you will be able to follow. But did you at least get an idea of how this Bode plot looks and how to plot the Bode plot? If yes, just put it in the chat box as yes, if you have understood.